Hi, welcome to Limits at Infinity. My name's Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. This lecture is for Math 1411 Calculus at UTEP. Chapter 3, Applications of Differentiation, comes to us from Larson's 11th edition calculus text. Section 3.5 is Limits at Infinity. So let's look at a definition of limits at infinity. Let's let L be a real number. The statement, the limit as x approaches infinity of f of x equals L, means that for each epsilon greater than 0, there exists an m, capital M, that's positive, such that f of x minus L has a distance less than epsilon as long as your x value is larger than m. So as long as x gets big enough, then my function value is super close to this real number L. And super close is what epsilon holds for us. Similarly, the statement limit as x approaches negative infinity of f of x equals L means that for each epsilon greater than 0, there exists an n, capital N, less than 0, it's negative, such that f of x minus L, that distance, is less than epsilon as long as x is small enough, right? Negative number, so it's small enough. So I could get my y values as close to this L as I want, as long as x is going to negative infinity, going to positive infinity. Once it gets big enough, let's see what big enough means. Alright, so why do we care about these limits at infinity? In pre-calculus, we talk about horizontal asymptotes and comparing the degrees of the numerator and the denominator, and that still holds. But there's also a reason behind it, and the reason behind it comes to us from calculus. The line y equals L is a horizontal asymptote of the graph if L is the limit at infinity. So as x goes to positive infinity, do the y values settle on L? Awesome. That's going to be a horizontal asymptote, and it's always the equation of a line. That is, one limit or the other, or both limits exist. All right? In math, or is always one, or two, or both. Theorem 3.10. This is a great theorem. It's kind of a lame name, but we're going to use it quite a bit. If r is a positive rational number and c is any real number, then the limit as x approaches infinity of a constant over x to the r is 0. Furthermore, if x to the r is defined when x is negative, then also as x approaches negative infinity, c over x to the r equals 0. Now, why would we have to say something like if it's defined? Well, if r is, say, 1/2, then I can't take the square root of a negative value, so it wouldn't be defined. But if r is maybe 1/3, cube root's no problem. So we just have to keep an eye on our domains and make sure everything makes sense. Here's some guidelines for finding limits at plus or minus infinity of rational functions. Wow, there's some bad typing going on. Let's see if I can fix that. There we go. If the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. And we'll prove this. The horizontal asymptote is the equation y equals 0. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. If the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. And that's the limit as we're approaching plus or minus infinity. Wow. Yep, that's really bad writing. At plus or minus infinity of rational functions. So let's look at an example. The limit as x approaches negative infinity of 5 over x minus x over 3. We're going to find the individual limits. The limit as x approaches negative infinity of 5 over x, a constant divided by a number getting super tiny. Well, if I have 5 M&Ms and negative 300,000 people want them, ignore the negative for now. Everybody gets essentially 0, nothing. You might get to smell the M&Ms, but that's about it. But if x is approaching negative infinity x over 3, that's not going to exist. Negative infinity over 3? That's kind of weird. So what does this arithmetic become? It becomes a 0 minus it doesn't exist. So the limit just doesn't exist. It's some type of infinity. We'd have to figure that out. Looking at the limit as x approaches infinity of x squared plus 3 over 2x squared minus 1, since the value of the numerator, the degree of the numerator is equal to the degree of the denominator, I should have a limit of 1/2. It should be the leading coefficients. That's what we learned in pre-calculus. Since x is going to infinity and it's not 0, what we can do is we can divide each term of this function by the highest power of x in the entire expression. And it looks to me like x squared is the largest power anywhere up here. So I'm going to take the limit as x approaches infinity of x squared over x squared plus 3 over x squared, all divided by 2x squared over x squared minus 1 over x squared. Why do I want to do that? Well, let's simplify it. X squared over x squared is 1 plus 3 over x squared. In the denominator, 2 minus 1 over x squared. And then we have the fancy titled Theorem 310. As x approaches infinity, this term will go to 0. It's a constant divided by x to the r. As x approaches infinity, this term will also go to 0. It's of the form c over x to the r, and x is going to infinity, and therefore the limit is in fact 1/2. So all those techniques we learned in pre-calculus still hold for calculus, but now we have a verification, a reason why. It looks like x squared is the highest power, but it's inside a radical. The square root of x squared is approximately x. So inside the radical we divide by x squared, and outside the radical we divide by x. I have to make sure I'm dividing everything by the same power. And inside and outside of a radical, I have to pay attention. So I'm going to divide the numerator by x. I'm going to divide the denominator terms by x, but since it's inside the radical, I'll rewrite it of the form x squared. I end up with a 1 in the numerator, a 1 in the denominator, plus 1 over x squared, all under a radical. As x goes to negative infinity, this term goes to 0. And I'll end up with 1 over the square root of 1. Notice that since x is being squared here, the negative, it's okay to have a negative under the square root of something squared. Something squared under the radical. A little bit of trig. Limit as x approaches infinity of cosine of 1 over x. Remember the limit goes through composition of functions. So as x goes to infinity, 1 over x goes to 0. Therefore, the limit as x approaches infinity of cosine of 1 over x will equal cosine of 0, which we all know to be 1. Just because it has trig doesn't make it hard. Get yourself out of that mindset. Sometimes these are the easier problems. But now, we're going to make it harder. The limit as x approaches infinity of 3x cubed plus 2x minus 7 all over the square root of x to the 4th plus 5x. Notice that the numerator has the largest degree of x to the 3rd, whereas the denominator has the largest degree of x to the 4th. However, the denominator is under a radical, so the square root of x to the 4th, that's like x squared. This means we'll divide each term by x cubed. But remember, when I divide by x cubed, in the numerator, no big deal. But under a radical, x cubed is the same as x to the 6th. So when I divide, I'll end up with 1 plus 2 over x squared minus 7 over x cubed, all divided by the square root of 1 over x squared plus 5 over x to the 5th. And I'm still taking the limit. I still have to write limit as x approaches infinity because I haven't let x go to infinity yet. But as x does go to infinity, this becomes 0. This becomes 0. This becomes 0. This becomes 0. And I end up with 3 over 0. And 3 over 0 usually does not exist. That's a great answer, and that'll work. But if we analyze this a little bit more, which I didn't do in the first example, as x goes to infinity, well, I know my numerator is going to be positive. As x is going to infinity, it's going to be positive. It's a square root. But 3 is positive. So positive over a positive, what kind of infinity is this going to be? It's going to be a positive infinity. So you could do further analysis. Instead of calling it d and e, you could determine that this infinite limit at infinity actually occurs. If we're looking at the limit as x approaches negative infinity of the square root of x to the 8th minus 1 all over x to the 5th minus 1, we compare degrees inside and outside of the radical. X to the 5th outside of the radical is comparable to x to the 10th inside the radical. So that's our largest term. I'm going to divide inside the radical in the numerator. I divide everything by an x to the 10th. Outside of the radical in the denominator, I divide by x to the 5th. And if I simplify, I'll have 1 over x squared, which goes to 0. I'll have 1 over x to the 10th, which goes to 0. And this is all good because a positive exponent under the radical, I could deal with the negative. If I had an odd exponent after simplification, I'd have a little bit of problems going on there. X to the 5th over x to the 5th gives us our 1. And 1 over x to the 5th gives us 0. And 0 over 1, no big deal. 0 over 1 is just 0. So this limit does exist, and it's equal to 0. That's it for limits at infinity. Thanks for listening.